Okay, we're now going to move on to lesson 6, which is ionic compounds. Um, there are some basic rules about ionic compounds. If you wanted to read about the properties of ionic compounds, you're going to be looking at about page 40, to 41 of your textbook, maybe even 40 up to 43 perhaps. It talks about the properties of, essentially it's going to be a summary of what I'm going to tell you, but it certainly covers more of the properties. I'm more concerned with the how and the why, but the properties are covered there a little bit. Now, there's one thing before I get into the one thing I want to say before I get into the student learning objectives. I want you to know when you have an ionic compound, this is a compound formed when a metal and non-metal transfer electrons. So this will make sense here shortly. But basically, I just want you to know when I talk about ionic compounds, we are talking about a metal and a non-metal coming together. The transferring of electrons you will understand shortly, but I think going forward, we have to understand or have the language that ionic compound means a metal plus a non-metal coming together. So that's the vocabulary that we have to have in common. The goals for the learning objectives for ionic compounds, lesson 6, is I want you to be able to write simple chemical formulas. I want you to understand the how, the why. I also want you to be able to name them properly. So we're going to go through this. I'm going to put together a number of examples. Now, some teachers might look at this and say, well, maybe he's not doing it 100% right. I am purposefully leaving a couple things out that I'm going to come back to later. It's all about building the process here. So bear with me. This will really help clarify things. And I think it's important to know that the 288 rule is fundamental to ionic compounds. So you have to ensure that you have that mastered. Okay, let's move along. Now what I'm going to do is I am going to take out my periodic table, and I'm just going to pick basic elements, and we're going to bond them together, and we're going to see if we can figure out why this would happen. Now again, this is where some people are going to look and say I'm doing this wrong. I'm doing something wrong on purpose. I'm not going to really make a big deal about it, but it's going to help us out big time. All right, so let's do this, everybody. Let's do sodium plus chlorine. So here's what we're going to do. We have a metal. We have a non-metal. Let's do the 288 rule of both of these. So sodium, as you know, let's kind of go down here. Let's look at the atomic number. Sodium has 11 protons. Let's put the electrons above. So we know we have 2, 8, 8. I need you to put 11 electrons in there. Remember, we fill from the bottom. So I can put 2 electrons there. So if I had 11 electrons, I took away 2 of them, I should have 9 left. Okay, I can put 8 of them there. I've used up 10. So 11 take away 10, I should have 1 left. Okay, let's do chlorine now. Oh, sorry, I'll put Na there. Chlorine. Chlorine is Cl. It has 17 protons. Let's do the 288 rule. This one's going to almost fill it. I can put 2 electrons there. I can put 8 electrons there. I've used up 10. So I have 7 more to account for. Okay, now hopefully you can see what's going to happen. Let's look at sodium at the very top. We know that this is not happy. And I told everyone that we have 2 choices. We could bring 7 in. We could get rid of 1. Well, everything here is lazy. It's easier to move 1 than move 7. Okay. Let's look over at chlorine. Look at the top level. Those valence electrons are not happy because, hey, it's not happy. So what are we going to do? Are we going to bring in 1 more, or are we going to lose 7? Well, everyone here is lazy. So I'm hoping what you're seeing is there's a connection here about what's going to happen. We've decided that we don't want this 1 electron here. But guess what? The chlorine will take it. That is a transfer. The electron has moved, physically moved, from the sodium to the chlorine. So basically, what's going to happen now is this is the new way it looks. So here's my sodium. It still has 11 protons. Remember, they don't change. 2, 8, 8. Well, we still have 2 here. We have 8 here. But now we have nothing there. This level's done. If you look now at the chlorine, number of protons sure hasn't changed. This level still has 2 electrons. This one still has 8 electrons. But now the top level, it now is perfect and it has its 8 electrons. This has now formed a compound. We have an ionic compound. The Na and the Cl have bonded together because of a transfer of electrons. Why did they transfer? It all comes down to the 2-8-8 rule. The sodium was unhappy. It wanted to give 1 away. The chlorine was unhappy. It wanted to take 1. It's a perfect match. That's an ionic compound. I'll give you another example. Let's go magnesium. Let's go magnesium plus oxygen. Okay? So let's do the 2-8-8 rule. So magnesium has 12 protons. Let's fill out our 2-8-8 rule. 2-8-8. So 2 can go there, 8 can go there. Well, that's not going to be good. And then we have oxygen. Oxygen has an atomic, let's see right here. That's going to be 8 protons. We can put, 2, 8, 8. 2 electrons go there, 6 go there. Well, I like to start doing this a little bit quicker. If you look at this top level, these valence electrons, you have a choice. This level wants 8. I could bring in 6. I could lose 2. Losing 2 is a better option. If you look right here, this is not happy either. You could bring in 2. You could lose 6. Well, that's no good. Hopefully you can see what's going to happen is there's going to be a transfer. These 2 electrons, they got to go, and they are perfectly welcome right there. The new reaction here, the new compound, if we look at magnesium, still has 12 protons. It's just the levels of electrons that have changed. So 2 electrons in that one. This one now has 8 electrons. Those are all perfect. This has 0, so we're happy. Now the oxygen has changed a little bit. It still has 8 protons. Now, 2, 8, 8. There's 2 electrons. Now, hey, we had 6. We got 2. Perfect. Don't need that level. Perfect, 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 perfect. That's your new ionic compound. We have magnesium and oxygen coming together. One lost electrons, one gained. And then here we go again. You're going to find a pattern here, everybody. I said to you earlier that, if you remember, metals, nonmetals, these are always positive ions. These are always negative. Can you understand why? Look at magnesium. It lost 2 electrons. Well, electrons are negative, everybody. They have a negative charge. If you lose something that's negative, you should become more positive. So metals always, they are positive because they lose negative electrons. Let's look at nonmetals. Now nonmetals, you'll notice in all of our examples, they're always taking electrons. They always take negative electrons. So if you take more things that are negative, you're going to become a negative charge. So we're kind of working on a process here. Okay, so hopefully you can understand where they were at. Remember, these were your atoms. But the atoms weren't happy based on the 288 rule. Then we had a transfer. The metal lost electrons. The non-metal took or accepted electrons. And if you accept electrons, you become... But the point is, everything's happy now because when one loses and one accepts, the 288 rule is perfect for both. Now, we're starting to move along here. Let's see if we can try to maybe do this in a quicker process. Okay? You don't always have to draw out all of these symbols. So, let's go with... Let's do calcium. Here's kind of a little more of the advanced way that you can move into. Let's look at calcium. And let's add it to, oh, I don't know, let's go with chlorine. Now, here's a much quicker way. You have to understand what I'm doing right now is a quick and simple way of putting together an ionic compound. But it's only possible if you understand the 288 rule and the rules we've been looking at. Look at your periodic table. Calcium has a charge of 2+. Chlorine has a charge of 1-. Now they're going to come together. Let's put CaCl. Now, the charges have to balance here, gang. If you look, I have 2 positive right here. I have I'm out of whack. So which one do I need more of? Well, if I have 2 positives, I better have 2 of these negatives. So I need to have, you put a 2 right here. Okay, you can just put these together. Because what we're looking at is just looking at the charges. So again, I'm trying to I'm jumping a step in the sense that I'm not making you draw out the 288 rule. But you should be able to understand that. So let's try another one here. Let's go with one more. Let's go with, oh, I don't know, we'll go, let's go potassium plus sulfur. Okay, so we're going to put K and S together in the very end. Look at the charge for potassium. That's +1. The charge for sulfur should be 2-. And I'm sorry, I do this wrong all the time. It should be 1+. Now, when they're going to come together, well, we have to have a balanced charge. So this is 2 negative. I better have 2 positives. So that means you put a subscript here. It means I need 2 potassiums to balance out the charge of the sulfur. And now it is ionically bonded. If you want to see it, here is potassium I'll do the 288 rule for it. It has, unfortunately I can't do that perfectly based on the 288 rule, but my point is, if I were to draw this out, at the very top it would have 1 electron in its valence level. And you guys know that that's not going to be good. Let's say it was 8 right here. Well, what's it want to do? Does it want to bring in 7 more? Or does it want to lose that 1? It wants to lose it. Let's look at sulfur. Sulfur has 16 protons. So this would go, what would it go? 2, 8, 8. It would go 2, 8, 6. Well, nothing here is happy, guys. Now, this is a bit of a challenging question because if you look at it, I think we know by now what's going to happen. This option is no good. This potassium wants to lose this. It's got to lose it. And we know, if you look right here, this is going to accept electrons. Now the point is, this 1 electron is going to go right there. If this 1 electron goes right there, how many electrons are now in this level? It should be 7. But you'll say to yourself, well, wait a minute. Well, that's no good. I'm at 7, I need 8. What actually happens in reality is another potassium would have to come along and it would have 1 valence level electron, and we know it would lose it. So guess what? That would have to go here as well. So this electron moved, this electron moved. How many are here now? Well, it should be at 8. So there you go. Now if you look at that formula, how many potassiums did we need? We needed 2 potassiums and 1 sulfur. I guess what I'm trying to show everybody here is there's a quick way, there's a long way. I hope you all can do, this is the goal. I want you to be able to do this, but you have to understand why we're getting there. I'll do maybe 1 or 2 more quick ones here and then we'll be able to move on. Okay, let's go in the middle. Let's just take something different. Let's go with, I don't know. Let's do cobalt. Pardon me, actually I'm going to change that. Let's go with, let's go with scandium. Now scandium is written as Sc. Its atomic number is number 21. Plus, let's go with oxygen again. Now, I could sit here and I could draw out the 288 rule forever, but I'm not going to do that. Let's look at the charge of scandium. It is 3 plus. The charge of oxygen is 2 minus. They're going to bond, and we're going to have an Sc coming together with an O. But the point is, you have to know how many of each do we have. Now, this is not as easy. You'll notice here, you can't just say, well, I'll take 1 more scandium. No. What I like to think of in this approach, when it's not just not straightforward with 1s and 2s. You might remember from junior high math, the lowest common denominator. What I do is this. I put the 3 in the denominator here, and I add it to this fraction with a 2. And you might remember when you do adding of fractions in math, you need to have the lowest common denominator. Well, the lowest common denominator in this case is 6. So how do you go from 3 to 6? You multiply it by 2. So that means we need 2 of the scandiums. Okay, let's go over. We're at 2. 2 times what gives me 6? It's 3. We need to have 3 oxygens. That's your ionic compound. We've balanced the charges perfectly. Okay, let's do 1 more of those that maybe they're a little bit trickier, I don't know. Let's try something, let's go with, I don't know. Let's go with iridium. Iridium is a metal, it's number 77. It has a charge of 4 plus. Let's add that to sulfur. Oh no, let's be crazy. Let's go with nitrogen. Nitrogen, as you might know, it has a charge of 3 minus. We talked about that earlier. Now they're going to bond IRN, but there's no way this is balanced. We don't have balanced charges here. Well, let's do the lowest common denominator method. The lowest common denominator of 4 and 3 should be 12. 4 times 3 gives you 12, so we need 3 iridiums. 3 times 4 gives you 12, so we need 4 nitrogens. We are now building simple ionic compounds. We started with the 288 rule, and we're now moving on to taking the charges and doing the math ourselves in our head. Finally, we're going to name ionic compounds. This is not a difficult concept. The rules for this, if you want to read in your textbook or how to do this, if you want to read it up again, it's on page 42. But basically, when you want to name it, there's a simple rule. Let's pretend that we'll do this most simple one ever. We'll put sodium plus chlorine. Now I could do the 288 rule, but if you look at your table, sodium has a charge of 1 plus, chlorine has a charge of 1 minus. Heck, I'm going to say it. If I did the 288 rule, it's because sodium has lost 1 electron and sodium has gained. Anyway, if you look, 1 plus, 1 minus, everything's happy. So there's no need to balance anything. Now, let's name it. Here is the rule. When you name an ionic compound, you simply write the metal as it is. So Na is sodium. Now, Cl, as you can see, is chlorine. What you do is you change the ending to "ide." So instead of chlorine, it's going to become chloride. Okay, sodium chloride. If I had, let's do another one here really, really quick. Let's pretend I had calcium coming together with fluorine. I would leave the front, so we have calcium. I wouldn't say calcium fluorine, I'd say calcium fluoride. It's very important that you know this because the naming of ionic compounds is quite straightforward and simple. One thing I want you to just know, you'll notice that, do you see this 2 right here? When I named this, I didn't put a 2 down here or anything like that. I just named them. The metal, you just name it. Sodium, calcium. The second one is chloride, fluoride. When you do ionic compounds, you do not account for numbers. And you're going to see we're going to do something soon where that does mean something. Anyway, everybody, this has been a very important concept. This is kind of telling you why a metal and a non-metal would come together. It's so important to be able to understand the 288 rule and why electrons are going from point A to point B. It's also important to understand that why metals are positive and why non-metals are negative. And then once you have that down, you can almost bypass that step and use the periodic table and the charges to predict your final compounds. Anyway, there will be practice on this. You may want to watch this video over again.